afternoon, everyone. My name is Laya. I'm studying in DSCS. And this is my teammates, Rishil TK, Durga Jayashankar, and Srihari. And our topic is determining the height of a spherical tank using the volume. Maybe you are not familiar with that, the topic. Maybe the next slide would be, this is our problem statement. Just have a look at it. In this, this is a spherical tank. Actually, we have to find, we will get the volume, and we have to find in this much of height, which is the mean. Sorry, how much volume is in this much height?
How much of volume of water is at a particular height? You have to calculate it.
It's in the reverse order. Like we have given this much amount of volume, and in which height will be, how much height will be it filled? Like that. It is not, we will be thinking like that, why we have to store it in a spherical tank? We have other shapes also, but it is mainly used for LPG gases. While storing LPG, it is difficult to store it in other shapes because of the pressure. In spherical, its pressure will be minimized. So, main aim. But here we are using a liquid water. Just go to the problem statement. We have given the equation of volume here, and we have to calculate the height. Also, we have given volume is equal to 30 meter cube, and also the radius of the sphere is 3 meters. We can rewrite the equation as V is equal to 30 equals divided by rewrite the equation as two 9 minus whole divided by 3 minus 30 equals to 0. Anyone have any idea about how to solve this equation? We have to find h. How can we solve this equation? Any idea? We have already studied the method. Yes. We are solving first it by using huh? No, it's just normal equation. I just substituted the or the given.
All the changes.
Okay. Write it over here. Equation. Just we can substitute this as, we only have a variable h. So we can write this function as f of h. So we can solve this by using bisection method. Everyone is familiar? Huh? This is a nonlinear equation, and also it has only a single variable. This is here. You can also use Newton-Raphson method.
Equation formula. Can you use quadratic equation formula? Is it a quadratic equation?
No, it's a
That's what I'm saying, like it's a moving equation. Therefore, it's very hard to do it analytically. Therefore, they resort to numerical methods. One of them method we are adopting first is bisection.
okay. Now we are using the bisection method. Everyone will be familiar with the bisection method, right? So our initial assumption is we already know the radius of the sphere. So it is 3. Take this as 0, then this will be the diameter, and this point will be 6. So I am taking my initial assumption as 0, 6. So first we have to check if the function is satisfying the condition for bisection method. So first we are representing x as 0. So f of 0 equals to, anyone can calculate this right now?
Minus x.
That is- and f of 6 equals to f of 6 will be approximately equal to 83.017. It satisfies our criteria for bisection method. That is, one point is negative and the next one is negative. So we have to find the next middle point. Middle point will be just to see 0 plus 6 by 2 will be 3. Then we have to calculate f of 3. We can also write it as tablet is as A B C is equal to A plus B by 2. Also find B tablets. First, we assumed A as 0 and we will be 6 by 30. 83.07097. And C is 3. And corresponding value for f of C. Can anyone calculate and just it's actually minus 30. Yeah, it's minus 30. So in next step, we are replacing 0 with 3. So A will become 3 and this will be 6. Then we have to calculate the next one. So next C will be equal to 3 plus 6 by 2. That is 4.5. And the corresponding f of x value is 65.
You can say the last one. You can say like again and delete the last one.
Okay. Like this wise continue, and we only get the correct value on the 26th iteration. It can be calculated using our Python code. And that topic will be covered by my teammate Rishi.
Have to start it. This one, I think all of the is this one equal to and this one. This one, no? Here? Yes.
This is the Python code for bisection method. Here we define bisection method. This is the function where we want to find the root, and a, b were the interval, a were the initial, and b is the final, and tolerance, and also the maximum iteration. The condition if a and if ab is greater than 0, there will place a value on that. And the different signs. Then we are saying iteration is equal to 0. Then we enter to a while loop where the condition b minus a must be greater than tolerance, where b minus a is the distance between the two points we are taking. In while loop, we put iteration to +1. Then assign c is equal to a plus b by 2, which is the midpoint. If this c is equal to 0, then return c is the root. If function a into function c is greater than 0, then we replace b as c, or a will replace to c. Then if the if condition, if iteration getting more than the maximum iteration, that we put 100, then it will be print maximum iteration reached, and it will be print. Then return, it will be print as a plus b by 2, which is the root iteration. Then we define the function as what we want to do. The 22 by 7 is the pi into h square into step 3 r here r step value, same value as
Additional number. Find the additional number. How can you write it? Find the additional number, right? Additional number, please. Input function of by inside the plus the to the power minus 4 and this should be correct.
Should we
correct
change
now?
now? Should we change now?
You can change now.
No, why?
Here 9 is 3R. Here radius is 6, 3. So we'll get 9 minus h by 3 minus 13. 13 is the volume. Then in root num iteration. Here the bisection method is a function. Is a function of which we want to find the root. And this 0 and 6 are the points AB. It will be prime the root. Print the root.
This is the output. So what is the conclusion? Yeah, what is the conclusion?
Should be the height for 30 meter cube.
Which is the root and iteration.
And you found the roots.
Where it is the height from where the volume given.
Excellent.
Okay.
My name is Sri Ahmed, and I'm currently studying in Digital University Kerala, doing my master's in data analytics with computation science. So my part in this presentation is to compute the previously done bisection method into Newton-Raphson, the same procedure in Newton-Raphson method. Okay. So everybody is familiar with Newton-Raphson method, so I directly go in for the computation part. Okay. So here so the volume of the spherical tank is V, which is equal to the formula of volume is pi h square 3r minus h divided by 3. And here we take the radius of that sphere as 3. So r is equal to 3, and we say the volume is equal to 30. And now we want to find the height appropriate for this volume, 30. As we all know, the equation of Newton-Raphson method is Okay. Okay. Equation for Newton-Raphson method is as follows, which is x k plus 1 is equal to xk minus f of x. K divided by delta x. X. So here we need to find the function formula. So here the function will be f of h is equal to the function is basically the formula of the volume, and also we like in add volume to the equation part. So we will get pi h square into 3r minus h divided by 3 minus volume, which is 30 in this problem. And after that, so we found this part, and the next part is to find the derivative of this function. So, okay. Sorry, I missed the part. I hope someone. Sure. We got 9 by multiplying 3 into 3. Okay. So next part is to find the derivative is equal to d by dh of 5 x square h by 3 minus 50. This is equal to we take out pi by 3, which is a constant, and we write it like this. We write dh of h square into 9 minus h minus d by dh of which is equal to this is pi over is this part, like this is a product. We need to find the derivative of this product, so we do the product rule. Which is equal to 3 into square plus 15 h minus 15 h square. Three plus 3 h square, which is equal to 5 h minus, we take out the h from both the terms, so we get which is equal to in this in 18 there is 3, and also in this term there is 3, so we take out 3, which is the common factor. So cancel out this and we get 5h into 6 minus h. So okay. Now I start the iterative process. Okay, then I first take the initial guess as 4. So I start taking h naught 4. So h1 will be h naught minus f of h naught divided by f dash of h naught, which is equal to 4. And I calculated this little earlier, so I got the answer as 53.809523 8 more divided by 5 point. Okay. Okay. Like this, so on. I got H2, I found H3 and H4. After H4, at the fourth iteration, I got the answer as 2.0264861, and after doing the next iteration, which is H5, I got the similar answer. So I concluded my iterative process, and I confirmed that H4, which is 2.0264, as the height of the spherical tank. I am handing this to my teammate Durga.
So good afternoon, myself Durga. So far we have discussed bisection method, we have looked into its Python code, and we have discussed about Newton-Raphson method. So now I am going to speak about the Python code for Newton-Raphson method. So first we have imported the required packages, which is NumPy, Matplotlib, lib, and math. So here NumPy is used for array operations, Matplotlib for plotting the library, plotting the graph and visualizing it, and then math for using pi value. And here we have defined the function and its derivative. Here define f function of x, which is equal to pi into x square into 9 minus x divided by 3 minus 30. This is the equation for finding the height of the spherical tank. And then we have got the derivative of it, which is equal to pi into x into 6 minus h, which my friend Srihari have already calculated. And now we'll plot the Newton-Raphson method and find its iteration counts. So here we have defined a function with name Newton-Raphson plot, and it has got the parameters function, derivative, initial guess, and tolerance we have set for e raised to minus 5, and the maximum iteration as 100. So here the function is this function which the user gives, and the derivative is this thing. Okay, then initial guess will give later on. So first we initialize the value into x, which means we assign the initial guess into x, and then we create a list called iteration values, which will contain all the values of x. This is used to plot the graph actually. And then we set the iterations as 0, which is used to find how much iterations we have used. And then we set a for loop and with the range of maximum iteration, which means this function will run until 100 iterations. If it goes beyond that, it won't return anything. And then we assign the function, which is this function that pi into x square into that function we assign into f of x and its derivative into dx. And then we have a condition which is we know the equation for Newton-Raphson, which is x minus f of x divided by f dash of x. So if f dash of x becomes 0 at any point, it won't work because the denominator will become zeros and that number is not defined. So we give that control command over here, which is if derivative of x is equal to 0, raise value error. Then next we have to find the which is x minus f of x divided by derivative of x, and we assign those values into x next. And then we append all these values, which is the x and the following x values into the previously initialized list, which is the iteration values, so that we can plot it properly. And then we set the value of iterations. We increment the iterations, which is after adding all the values to the list, we'll add the value of iteration. So after completing one iteration, this iteration value will become 2, 3, and so on. And next, if the current value minus initial value is less than the tolerance, which is e raised to minus 5, then this would break and goes out of the loop. And next, we add the value of x next into x so that we can continue the following iterations. And now here we plot the function. Here we got the x values as np.linspace of 0, 10, 400. So here it will create 400 uniformly spaced points from 0 to 10. We have already been familiar with the function linspace. So this will create 400 spaced values as x values, and we'll calculate the corresponding values by using the function. Like we've got the function over here. This is the function, and for each x value, the corresponding y values will be added to y values. And now we are going to plot the figure. So for that, we have got plot.figure. This command will create a new figure with dimension 8, 6. And then here we'll plot the function, which means we have got the x value, we have got the corresponding y values, and we'll label it as f of x. I'll show you that. Yes, here we are going to label it as f of x. And then along with that, we give the color as blue. So that's also over here. And then in order to plot the iterations, we have used the function enumerate. This enumerate function will give both the index and the corresponding values. And by this command, it will plot the middle values, actually, the x values actually, which means the first iteration, the initial guess is 4, and after the first iteration, it will become something over here, and that values will be calculated here, and that is given by this command. And next we have given the font size and all, and towards the end, that is used to this thing. Wait, I'll show you. This z order equals to 5 ensures that iteration, which means this thing, this iter, we gave that label, no, that is placed on top of the function so that we can see it. It's used for visualization thing. And then the font size is equal to 9 and all those things we give. And then here we plot the initial guess. That means the initial guess and the corresponding y value, and we give it the color as red. This is plotted over here. And then we got the title of the plot, and then the name of x-axis, y-axis, and the legend. Legend means this box. This is called the legend. And then we've showed the grid, and also finally we displace the plot. And in order to print the number of iterations, print conversion iterations, which means this value. We have already incremented the value after each iteration, and so the number of iterations will be stored in this variable named iterations that will be printed over here, and it will also print the root, which means this is here we again call the function which is named as Newton-Raphson plot with the parameters function, derivative, and initial guess. So it will return the root, and hence within 4 iterations we got the root. So basically we can say that we have seen the root converging only in 25 or 26 iterations or something like that. But when it came to Newton-Raphson, it came in 4 iterations itself. Hence we can say that Newton-Raphson is more powerful than bisection method. So that's about it. Thank you.
Good afternoon, everyone. We are group number 1. Myself, Aditya Jayasundar. This is Kavya. We are presenting on the topic Principal Component Analysis, PCA. Like as sir told in the class, he talked about something called as dimensions, and there are multiple dimensions, and researchers are all studying about different dimensions and how many dimensions can be visualized, black holes and something like that. So principal component analysis is something that deals with reducing dimensions of data sets. Like this is not exactly that dimension, but in talking about the point of view of machine learning or some data analytics, something, these dimensions are something that are features, columns or rows, attributes or something like that that are used while that we are giving as a variable as an input to the models to train on the data set. So these are the topics that we are covering today: curse of dimensionality and different dimensionality reduction techniques, principal component analysis, and its Python implementation. So dimension. What are dimensions? Dimensions are the number of input features, variables, or attributes that we are providing to our model to study about the data and give us the output that we require. So the problem statement that we have is curse of dimensionality. So the curse of dimensionality is something that I'll explain it with an example. Same page.
Sir, can you repeat this?
Blank page. It's just duplicating them. So think of it like different models. Like this is model 1, model 2, model 3. So we are inputting 5 features in this model 1, 10 features in model 2, 15 features in model 3, and maybe 50 features in model 4 and 100 features in model 5. And we have total 500 data sets. So when we are measuring the accuracy of these models, the model 1 will have accuracy 1, accuracy 2, and like this. As we can see a graph of like this, like as the accuracy, as we increase the number of dimensions in a model, we can see that the performance tends to decrease after a certain break-even point. That this is exactly called the curse of dimensionality. Like after a certain point, we can see that in our example, maybe the model with only 3 features that will give us a good accuracy, and even the model with 10 features that will give us a better, more accuracy. And after a certain point, after 15 or after 50 or 15 or something, we will lose our accuracy, and the model will perform overfitting, and it will give the more R-square value, and the model will not perform that much. This is exactly called the curse of dimensionality. So this is the problem statement that we took, and the other methods are described by Kavya and Amal.
Coming to Kavyashree from DACS. So coming to dimension reduction, you saw that curse of dimensionality, right? Like we are having, like we can't plot that, like we can't visualize that. So we'll reduce the dimension to get visualized in machine learning. So as Aditya said that, like what are dimensions? Like, can anyone tell what are dimensions? Okay, I'll tell you example. Our data set. Suppose if we have our class data set. So we'll have some variables, right? Like serial number, and roll number, name. What else we can have? Okay, suppose we want some result. Okay, like our target variable. Let us assume that it is a pass or fail. Like how many students have passed in our class. So we'll take subjects. Suppose computational science and computer science, etc. And last, we'll take percentage and pass or fail. Okay. So we don't need these many variables, right? Like we are having, but we can't represent these many variables we can't visualize that, right? So we have 2 techniques for dimension reduction. One is feature selection and one is feature extraction. In feature selection, what we'll do is like we'll take subset of that features, what we have. And in feature extraction, we'll extract what we need from that features, okay? So in feature selection, we have 3 methods: filter method, wrappers, and embedded. In filter methods, we'll take the best subset of among this. So what the best subset in this variables are like percentage and pass. Like they are correlated with each other. Like if the percentage is about 40 or something, then will be pass or fail. We can. So in wrappers method, what we'll do is like we'll find the subset of the data set using chi-square method, ANOVA, and all. If the p-value is less than or equals to 0.05, then it is like they are correlated, and we can we can take that subset. If the p is greater than 0.05, then we can say that like that is not correlated. So we can just ignore that. Coming to embedded method, it'll consider iterations to find that subset, which is the best subset. And in feature extraction, we use principal component analysis and linear discriminant analysis, and we use many methods to extract features from the dataset. Now, principal component analysis will be taken by Amrita.
So, hi everyone, my name is Raman, and now I will take the part of principal component analysis. So, what we studied so far is like what is basically a dimension is. So, what dimension is like, suppose we having a large data set, we having a large number of columns. So, this basically the large number of columns representing the dimensions of a data set. But what happens is when we are training any machine learning model, what happens is when we are training a model, when we have a large number of features, the performance of the model will decrease. So that basically the problem is we are trying to reduce that features, that dimensions. We are having thousands of features, but we are trying to reduce to 50 features, 100 features, which are just important to us. Not we are dealing with thousands of features. So that's basically the problem is. That is a curse of dimensionality. Actually, we are not able to visualize it like this. So if we are plotting high dimensional data, so it should be like that. We are not able to visualize basically what are the classes, what are the different categories. So our data is something like that. Now, dimension reductions. So as Kavya said, we are having two techniques to reduce dimensions. First is feature selection and feature extraction. So before coming to PCA, principal component analysis, which is coming in the feature extraction, I just want to take an example to explain basically what is the intuitive behind a PCA. So let's suppose I will take an example. Like there is a photographer in a stadium who is taking a picture of a match. The stadium is in 3D, but the picture he is taking is in 2D. So what he did is he trying to represent that 3D stadium in 2D. So what basically PCA does? PCA represent the high dimensional data in 2D. So this is the main objective of principal component analysis. And take one more example is like when I will give you a book of 300 pages and you can't read 300 pages, instead of I give you 1 to 3 pages of summary, it will represent the instance, entire book. It will represent the instance, all instance of the whatever is written in the book. So this is what basically PCA does. And principal components. So let's take an example. Let's suppose we having one. Let's suppose we having 3 features. One feature is like suppose we having a retail house data set. Which is related to real estate. Suppose the first feature represent number of rooms and the second feature represent number of grocery shops. And the third feature, basically the target value, which is price of the house. So it's a house data set having feature number of rooms, and the second feature is basically number of grocery shops around the house. So the price of the house will depend determined by these two features. But if I ask you which is the important features in these two, number of rooms or number of grocery shops? Which feature is important for predicting the price of a house? Number of rooms or number of grocery shops? We having a house data set having two features or two dimensions or two columns. One is number of rooms, and the second is number of grocery shops around the house, and the third one is price, which is determining the house of a price. So I just want to ask which feature is more important for you, number of rooms or a number of grocery shops? Right. We are selecting one feature out of it, number of rooms. But the thing is, there are only two features. But if we having a large number of features, like we have number of rooms and number of grocery shops, there might be some other features. But how can you determine which feature is important for you? So there is some trick or some mathematics behind it. What we did is we just tried to plot it. So this is number of rooms. This number of grocery shops. So if we plotted data, we will like data should be something like that. So what we did is we are trying to project this data on the two axes. The axis which having the most spread of data, that axis we select, or that feature we select. Axis the present number of grocery shop. So here we are selecting number of rooms as an important feature. So this is what feature selection does. But now I'm coming to feature extraction. That's basically what feature extraction does. Feature selection select features from already existing features, subset of that features. But what feature extraction does is feature extraction take all the features as a combination to extract new features. Like suppose now we have number of rooms, number of washrooms, and the third column is price. Now in this case, both these features are important to determine the price of a house. So here feature extraction comes. So if you ask any real estate agent, which feature should I take to predict the price of a house? So what he says is, why you're taking these two features? Just take the size of a flat or a house. So these two features are now representing by the size features only, just one feature. So we are reducing these two dimensions into one. So now this size feature only represent the whole, that will determine the price. Now if but how can we plot it? I can show you. This is number of rooms. This is number of washrooms. Now we have to select one feature. We have to determine one feature. So what we did is we plot the data. This data could be something like that. Now if you see here, if I project this data, the spread of data on both sides are equal. that represent both the features are important. What we are doing is we are trying to find one more axis or one more feature that will represent the entire instance of data. So we are finding this axis. One more axis or one more feature that will represent this data. So if we project this over this, so here now this variance, this is new feature that we found, which we got principal component as a part of principal component analysis. This is the new feature we found out of these two features. And now if you see the projection on this axis, now this is less. Here is the more spread of data, more representation of data, and here is a less representation of data. So basically what PCA does is trying to reduce the highly correlated features into uncorrelated features which are perpendicular to each other, which are orthogonal to each other. As I mentioned here, first of all, principal component analysis is unsupervised machine learning algorithm, which is trying to understand the data by itself. No supervision is needed as data is not labeled. And supervision means like we doesn't need any kind of supervision. Found one new feature out of the two features. Here we reduce the features 2 dimension to 1 dimension. We can say. So here I mentioned this picture, which is in 3D, and I reduce this into these two features in 2D code. Yeah, sweet. So basically what it is this is the last principal component analysis. We are having this axis, these two features, which is representing the initial data. After that, we are trying to find one feature that will represent the entire data. This is just one feature. This 2D, we are going to 1D as an example, but there's more features. So basically, our principal component analysis is a statistical process where we are converting highly correlated features into uncorrelated feature through orthogonal transformation. As we studied that, we did some kind of transformation, like if we having a matrix A, so if we have a matrix A and we multiply it with a vector, it will do some transformation and it will increase the vector strength. So we are trying to find that vector which will represent the maximum spread of data. This will be the principal component. But in PCA, what it does is we apply PCA. So what PCA does is we having an objective function in PCA, but this mathematics is a little complex. So what PCA does is try to solve that function, and so that function you try to find covariance matrix. And that covariance matrix we are trying to reduce to eigenvectors, and that eigenvector is the one which will represent the particular feature. This feature. This is the direction. And we project this data on this feature, and that will become our new component or a new features of our data set. So now we move towards the Python implementation.
So, hello everyone, I am Ankit and I'm here to present this PCA Python code. So firstly, we will go with importing the pandas library, NumPy and Matplotlib library. Then what we will do is we will create a data frame which is named as df, and it will import a data set called irisdataset.csv. Then we use this head function here. Head function, what head function will do is it will compress the data in only a 4 to 5 column data file, and after that we will assign that a new variable called x, in which this location of the indexing is given to this df data frame. After that, we will plot this iris data frame using this scatter function. So here we imported the, from SQL and pre-processing, we imported the standard scalar collection of functions, which is used for pre-processing functions used to transform raw data, and here used to reduce dimensionality of the data. Now we use the SC fit transform function. Where the fit transform function what do is it does the scalar data and transform it into a single step. Then what we have created is we have named the columns of this data frame into new column names called sepal length, sepal width, petal length, and petal width. So for determining the covariance, we use the covariance function called COV, which is a function of NumPy library. Then we use NumPy library linear algebra function to import the EIG function, which will give us the eigenvalues and the eigenvectors using that covariance matrix function. So here we got 4 eigenvalues and 8 cross 8 matrix of eigenvectors. After that, we sorted this eigenvalues into descending order to ascending order, where you can see this array output you are seeing here, this one. After sorting the eigenvalues, we will sort the eigenvectors into the sorted index which is required. After that, we will find the sum of the eigenvalues, and we will try to find the variance of each data eigenvalues using the percentage of the variance of each feature is found out here. Then we will print the variance of each feature, where variance of each feature is printed out in this area. After that, we will find out the cumulative frequency using the CumSum function of the NumPy library. Then we assign the eigenvectors into a new feature variable by slicing it into only 2 columns. Then we created an eigenvector subset which sorted the eigenvectors by the slicing concept of NumPy. And then we checked the shape of the data set, which will give us 150 rows and 4 columns. Then we reduced the data set into 150 rows and 2 columns using that np dot function. Then we created a new data frame using the old data frame by copying its two columns called PC1 and PC2. And then we concatenated a new target column which will store the Iris setosa, Iris virginica, and other type of irises in this target column. Then we will import the Seaborn library to see the visuals of the graph. Then we imported the matplot library for importing the plot function. Then we use the plt.figure function to plot this graph here. Then we have given the 5 width and 5 height. Then we use the scalar plot function to define the x and y axis as named as PC1 and PC2, where we have defined this 3 types of irises in this area: Iris setosa, Iris versicolor, and Iris virginica. Then we are importing the scikit-learn here from this library, sklearn, where we imported the PCA function, and then PCA function is assigned to an object named as PCA. Then we transformed this x.st data frame and fit and transform into a single data set into a single step. Here PCA.reduced is a new variable in which we define 2 components using the argument of the function PCA. And then once again we fit and transform with a single step of using the fit transform function, and the same data set is assigned to a new variable called PCA new. Then we printed out that PCA.reduced file using the print function. Then we have checked out here the shape of the data set, which is reduced from 150 rows and 4 columns to 150 rows and 2 columns. Then here we are creating a new data frame to reduce data set, new PC.df. Then we are concatenating with target variable by providing axis1. Axis1 means providing the column here. Then we imported the Seaborn library and SNS function from Seaborn library and matplotlib library and function plt to give the figure size of 5 width and 5 column, 5 width and 5 height. And then we scatter plot this this figure here into x and y axis, which are named at PC1 and PC2. And this is the graph. This is the scatter plot we have given here.
That's all. So I hope you understand what PCA is. So guys, you know what's the basic objective of PCA? Anyone? What PCA does? As you understand what PCA is? Actually, PCA is a little complex topic, and the maths behind it is little very difficult. So what basic is we are trying to what PCA does is the first seed in Python is like we having a data set and we are trying to find a covariance matrix, and that covariance matrix results into an eigenvectors and eigenvalues. And here the concept use of dominant values of eigenvalues. And if through this we are trying to find the dominant values of eigenvalues, which the dominant values and corresponding eigenvector, and the data set we have, we are trying to project that data over that eigenvector, which is a dominant eigenvector, and through that we get new features, which will reduce from 1000 dimension to 2 dimensions. So that's all about PC. Thank you.
No, they don't have it.
So where is the recording?
No, just wait. Just this one. This mail, can you open? Yeah. Me first.
Good afternoon. We are group 7. Myself Neha from DACS, and these are my teammates Arshida, Shreya, and Anshif. Our topic is time series forecasting by polynomial extrapolation. This presentation will explore on what is polynomial extrapolation, its method with an example, and practical applications. Practical application. Our presentation will explore on what is polynomial extrapolation, its method with an example, practical application, followed by Python implementation. Introduction. In data science, extrapolation is a statistical process which constructing new data points outside range. Extrapolation is similar to hypothesis involving the use of facts or observations of a known or present situation to predict future outcomes. In data science, extrapolation is a statistical technique which employed to estimate a data point beyond a range covered by known values in data sets. The widely used methods are linear extrapolation, which uses a linear equation and it uses points in graphs. Polynomial extrapolation it involves fitting polynomial functions to a set of time series of data points. This function is used to predict future values, as we can see in this graph. Polynomial extrapolation is typically done by means of Lagrange interpolation or Newton's method. The basic advantages are its computational simplicity, transparent methodology, and low data requirements, and also it's flexible. It can use different complex patterns to predict future outcomes. Over to Ashita.
Shida. I'm talking about the method calculation to polynomial extrapolation. First, we are the preparation for the data, prepare the time series data to identify the time period and corresponding values for the variables you want to be forecast. Then the polynomial fitting, repeat a polynomial function. A higher degree polynomial can be data more precisely. Then extrapolation, use the polynomial function and estimating the value of outside the data set. Then evaluate and comparing the polynomial predicted value and known value. Then we get the error. Let's do an example. Here the data set x is 1, 2, 3, 4 and y 3, 5, 9, 15. First of all, we fit with a quadratic equation. Please. So we select the polynomial equation, substitute the value of the x and y. We got a 3 equations and solving the equation by substitution, elimination or metric operation. Then we get the coefficient of the polynomial equation A, B, C. Then that's this data set. We get the coefficient A equal to 1, B equal to -1 and C equal to 3. Substitute the coefficient to the polynomial equation. Then our polynomial equation is y equal to x square minus x plus 3. So we get the polynomial function. Then we try to extrapolating value outside the data set. The question, we want to estimate the value of x is equal to 6. Then we put the value to the equation. By polynomial extrapolation method, we are estimating the value of x is equal to 6. That value is outside the data set.
My name is Mohammed Al-Shif. I'm explaining the time series for forecasting by polynomial time series extrapolation. It involves the fitting of a polynomial curve into historical data, and then using the fitting, and then using the fitting curve to predict the future value. These are 4 of the steps: gathering historical data, fit a polynomial to the data, find polynomial coefficient, forecasting future value, and explain one by one. First is gathering historical data. That means collect the time series data such as like stock price, sales figure, etc. or a time t. That is t1 by this t is represented by the time, and y is equal to the observed value at each time on point. The next step is find a polynomial to the data. A polynomial has a degree in the form k. Then the y is equal to k equals to k plus this you can choose the degree of the polynomial based on the behavior of the time series. A higher degree polynomial may be fit into the data. That may be more accurate, but it is it's not. And another step is find the polynomial coefficient. Using regression techniques such as least square to determine the coefficient A0, A0, A1, etc. to AK. By using this process can minimize the error between the polynomial curve and the actual observed data. The last one is forecasting future value. Once a polynomial is fitted, used to extrapolate the future point. For instance, to predict the value y at a time, tn plus 1. Substitute this tn plus 1 into the polynomial equation. And when to use is when it is used the time series forecasting. When the time series shows a smooth trend, or when the short-term forecasting is sufficient, when the relation between time and the values is expected to follow a simple polynomial pattern. And one is application. There are many applications. First one is sales forecasting. It predicts the future sales based on historical sales data, helping business plan, inventory marketing, campaigns, and resource allocation, and financial modeling. Forecasting stock price and interest rates and other financial variables enable investors to make informed decision. The other one is the prediction, predicting the temperature, precipitation, and the weather parameter, and disaster preparedness and resource management. Last one is population growth, predicting the population growth pattern, assisting in urban planning, infrastructure development, and resource allocation. Over to the screen.
Now, my name is Raya. So I will be explaining the code for polynomial extrapolation. So we use NumPy and Matplotlib libraries to plot this code. NumPy is mainly used for numerical operation and Matplotlib for plotting graph. So sample the data points. So we are giving the data as an array. You can see it in 1 to X data and Y as 3, 5, and 9, 50. We are giving this as an array. So next step is to an polynomial. So we are using polyfit function. This function returns a coefficient which is suitable for these data points that we are given. So we are given these data points as X and Y, and 2 indicates that our polynomial is degree of 2. We are using poly 1D function. This function returns a polynomial object that is used for evaluation, for further evaluation in our code. Next step is to generate new x values and y values. So in extrapolation, we create new values for outside our range. So x new, we are giving these ranges as 6, 7, and 8 as array, and we have to find the y values x new into the y values as in polynomial function. Next is to plot these data. Plot these. So we are using PLP scatter. So first we are plotting the original data points. The original data points is marked as red dots in this figure. Extrapolated points, that is the y values that we have finded. Then these orange is our polynomial. So this is a code for polynomial extrapolation. Thank you.
Presentation.
Last one.
Of polynomial extrapolation. Since this technique is powerful for time series forecasting, but it comes with its own limitation. So first limitation is it is sensitive to outliers and noisy data. So it may lead to inaccurate prediction. When higher degree polynomials is being given to this function, it might capture random fluctuation and which leads to overfitting. These are its limitations.
In today's fast-paced world, accurate forecasting with polynomial extrapolation plays a crucial role in various fields from finance and economics to climate change, as it has its own advantages as well as disadvantages. Prediction totally depends on the quality of data. These are our references. Thank you.
End the meeting.